Earth is awash in a sea of humanity. We have assumed control over nearly every facet of the world and replaced the natural order with our own. But modern science is restoring our connections to the animal world. We are learning that some of the most ancient animals first employed talents and powers we use today.
This simple little creature is giving us a lot of insight into how we evolved.
What do humans have in common with this bizarre array of animals?
Evolution has changed. It's changed over time. It's really interesting to me as a scientist to tie it all together.
Now we have a very much more detailed story about vertebrate evolution than could ever have been imagined by Darwin. He would have been completely delighted to see what was going on.
Join us as we meet some unique creatures who are more like us than we could ever imagine. We'll unravel the twists and turns of evolution that led to our existence. This is our place in the shape of life. From the beginning of human history, people have sought to explain our place in the world. An age-old Hawaiian chant, Kumulipo, describes a connectedness, a belief that human beings are related to all the creatures of land, sea, and sky. In a world of machines and technology, human beings often seem divorced from nature. But perhaps the natural world is not so separate from us. Scientists have found new evidence linking humans to the simplest of creatures. These discoveries confirm age-old beliefs in the unity of all life. Many human abilities can be traced back to some of the earliest animals on Earth. Sponges might seem like unlikely ancestors, and yet, over 500 million years ago, they were the first animals. We have inherited the chemical language first spoken by their cells. Early creatures like jellyfish and anemones were the first animals to harness muscle and nerve. Their basic architecture for movement has been passed along to us. A small worm-like creature evolved the first head and the first brain. It was the first animal to move through the world with direction and intent. It could hunt for food and for mates. We have inherited these powers from an ancient worm. If animals like these were our earliest kin, what other strange relatives do we have in our family album? Biologist Linda Holland is on the trail of a distantly related cousin. A trail that takes her alongside a modern thoroughfare. With trucks leaving Tampa Bay passing overhead, her hunting grounds are something less than glamorous. The Courtney Campbell Causeway isn't high on the list of Florida's tourist attractions, but for Holland, there's a powerful lure. She travels here to collect simple fish-like creatures with which we have a surprising amount in common.
Where we collect the animals is off a causeway that was built across Old Tampa Bay in the 1930s. And sometimes when you build a causeway, you change the ecology of a location.
In this case, changing the ecology was a boon for one tiny hero called Amphioxus. The causeway shifted the currents, depositing a great deal of sediment. These sandy shallows are the perfect place to hide from predators, and Amphioxus make up over 70% of the animal life in this sand. Their bodies are tiny, but they hold enormous secrets. Their early relatives brought something new into the animal world, something not altogether obvious. And that's why Holland's team is shoveling sand. It doesn't look much like high-tech science. But in the murky water and sediment, there may be a gold mine of hidden information. Back in her lab, Holland eagerly awaits the day's catch.
Okay, well, let's see what you've got here. Well, that looks like a pretty good collection.
This diminutive creature tells us volumes about our own evolution.
Males in one dish and females in another.
Without eyes, ears, or jaws, this is a very simple organism. Yet it has some surprising things in common with us.
Amphioxus is giving us a lot of insight into how we evolved. We're interested in it because back in the fossil record, there were little organisms that looked very much like this. So by studying the modern-day Amphioxus, we can begin to reconstruct a scenario, a scene for exactly how the vertebrates evolved from little invertebrate creatures like an Amphioxus.
The ancient animal revealed in this fossil is a dead ringer for Amphioxus. It is called Pikaia. It lived over 500 million years ago when an explosion of life took place in the oceans. This event produced every animal group on Earth today, including the one to which we belong, the chordates. No more than a few inches long, Pikaia and Amphioxus are minuscule compared to humans. But both the extinct Pikaia and the living Amphioxus have some body equipment oddly like our own. Like Pikaia, Amphioxus has a nerve cord which relays commands from the brain. It has gill slits, just as human embryos do. It has segmented muscles that allow it to move, but the real innovation was the notochord, a stiffening rod reinforcing its shape. This was the precursor of a backbone. We carry vestiges of a notochord, the discs in our spine. Our spines place us in a special group of chordates called vertebrates. The backbone is the crux of every vertebrate body. It is the central scaffolding of the skeleton. Now, Linda Holland's team is searching for another connection between human beings and Amphioxus. In the steamiest stretch of the summer, Tampa Bay hosts an annual convention. Beneath the dark surface of the water, an orgy is taking place. Amphioxus is spawning down there, and Holland's team is trolling the shallows to gather embryos. The embryos drift in the plankton, practically invisible to the naked eye. The water brims with millions of them. An embryo is an animal under construction. It reveals secrets you would never be able to see in an adult. But those secrets won't be visible for long. Holland compares the genes of this simple animal to other chordates, including us.
During the first 48 hours, these embryos go from a very tiny egg about the size of a pinpoint to a swimming, functioning larva with a mouth capable of moving through the plankton very rapidly. By studying the genes that are involved in shaping this embryo and comparing the genes to those of animals higher and lower on the evolutionary tree, we can say a great deal about the evolution of body form.
Holland is studying the genes that are activated during the crucial early stages of its life. The first time she compared Amphioxus to vertebrates, she made a dramatic discovery.
One of the most exciting moments was when I got the very first pattern of where a gene was turned on in the nerve cord of an Amphioxus, and it was just the same as in the mouse nerve cord or the human or the chick nerve cord. And I thought, this is going to be really exciting, and it just opens a whole new field for us.
Holland's discovery meant that a creature much like Amphioxus was an ancestor of human beings. The same genes direct development in Amphioxus and every other animal with a backbone. All vertebrates have common ground with Amphioxus. But how did we become so much bigger, so much more complex?
Vertebrates really became big dominant animals by getting extra genes, because an Amphioxus-like organism has relatively few genes. It has the same number of genes as your typical worm, your typical ant, your typical fly. Whereas vertebrates have done something rather special. They've taken this basic number of genes and they have simply duplicated them. Not once, but twice. And then they've changed them just a little bit. You suddenly have 4 times as many genes linked together to make brand new structures.
The quadrupling of genes led to the big animals that are the stuff of nature channels everywhere.
Having extra genes has allowed the invention of very new things such as neural crest cells.
These remarkable cells actually migrate through the embryo, helping to create new structures like the skull and jaws.
Once jaws evolved, then the animals could switch from eating microscopic plants to something like becoming a predator and eating other animals. And therefore, the animals could increase their body size. And so we went from something as small as an Amphioxus to something as big as elephants and cows and horses and lions and tigers.
Long before big mammals, fish were the first animals with bony jaws. In a world of spineless creatures, they flourished and dominated. Having more genes turned out to be something that fish could really grin about. Fishes developed all kinds of skull and jaw structures. Flexible jaws mean a wide mouth. Fish could make a fast meal of larger, more nourishing prey. Jaws helped them to become the most gigantic creatures on the planet. The most feared jaws of all allowed sharks to chomp their way right to the top of the food chain. Skulls protected the soft brain as it became larger. Fish became the geniuses of their time. But evolution is not a straight march forward. Without the fourfold increase in genes, some chordates would follow another path, living lives radically different from our own. Tunicates, fixed to the rocks, still laboriously siphon the waters for food. They may lack backbones, but they are related to us. One of our strangest relatives is the salp. They are small, about the size of a human hand. But when they reproduce, they string together like a wandering strand of pearls. This diaphanous cloud is secreted by another of our obscure cousins, a larvacean. The porous walls of its home allow tiny food particles to flow into an inner chamber where this blue, wispy animal feeds. While it lacks a fish's head and jaws, this is a real predator, a tunicate able to capture living prey. Rooted in place, it releases its trap in slow motion. These simple animals have remained in the sea. Fish, with more genes, were ready to take the next step, literally. The next step would be monumental. But it would take more than flimsy fins to carry fish out of the water. Cambridge, England, is home to an extraordinary creature, a missing link between fishes and us. Paleontologist Jenny Clack has spent her career in passionate pursuit of the first of our relatives to walk out of the water.
I study the earliest tetrapods, and tetrapods are creatures with 4 legs and fingers and toes on the end of them. And I'm also looking at the transition that those animals made from living in the water to living on land. It's every paleontologist's dream to find a transitional form, something that falls between 2 groups that we're familiar with, sort of links them both in its anatomy and also in how we think it lived. When we first collected it, we suspected that we'd got something exciting because we could see lumps in the rock, suggesting that there was more to the specimen than met the eye, and we could see across cracks, suggesting that there were things inside waiting to come out. Because when we fetched it from the field, most of this surface was covered with rock. It's had to be dug out bit by bit.
Clack and her associate Sarah Finney have studied this one remarkable fossil for years. It was a fish-like animal with limbs.
Well, what have we been working on today? We've been working on neural arches.
The same kind of structures that would eventually carry us onto land.
Peculiar one goes. I think this is a specimen I called Boris, and it really could be described as a missing link, except that here we have it. It's a transitional form between animals with fins that we would call fish and animals with legs with fingers and toes on the end that we call tetrapods. We're tetrapods.
Boris walked a fine line between being a fish and being a new kind of animal.
We've got a skull attached to a vertebral column which goes through this S-bend like this and goes off into the tail here. And then here is the forelimb, one of the forelimbs, and some digits here.
Although it's got 8 on each limb, Boris bears early versions of our fingers and toes. We share other structures with Boris.
If we look at the back of the skull here, there's a rod-like structure here and here. And if we turn the skull over, you can see grooved rods. And that means that there was an artery running up that groove, feeding the gills blood so that the blood could be oxygenated. And that factor suggests that the animal was still using gills to breathe. It would have had lungs anyway, because most of these early fish did. But this animal was using both gills and lungs, unlike later tetrapods, where the gills are lost.
With both gills and lungs, it could breathe oxygen in water and air. Boris displays evolution in mid-process, even though this species disappeared.
I like to understand the animals. I like to know what went on, and I suppose one of the greatest frustrations for people like me is that you can't simply get into a time machine and turn it back to the Devonian and go and have a look. I'll never know what colour its eyes were, for instance. But it's trying to understand what the animals were doing and what life was like back all those millions of years ago.
Valencia Island, off the southwest coast of Ireland, actually is like a time machine for Clack. Primeval footprints have been discovered here on the island, the marks of some of the earliest footfalls.
A couple of 100 yards here at the water's edge.
They're just over there?
They're just over there, right on the water's edge, on a flat slab of rock, quite easily seen.
Clack has spent decades deciphering fossils. Now, for the first time, she makes a pilgrimage to see if the early footprints can reveal the way our first limbed ancestors walked.
It'll be a bit of a scramble. A little bit slippery, I guess, down there. The grass is very wet. Where do we go? Hey, look. Oh, wow. That's amazing. We've got several here. We've got this big one here coming out of the rock. And then here's another one, which is rather different, differently spaced. And then you've got a whole trail going out across the platform there. You can see the belly scrape there. Okay, what's the measurement across there?
The identity of the animal who walked here remains a mystery.
Okay, yep, got that.
But its abundant tracks allow Clack to speculate on what it was doing on this patch of mud one day, millions of years ago.
223.5.
Okay.
So it's pretty amazing, this, actually. Which direction do you think the animal was travelling in?
I think it was coming out from under there and coming out around here and going out that way. So we've got a whole sweep coming right from over there, round and going off into the distance there.
And do you think it was in shallow water, or...?
Well, I think these animals would have been definitely sort of semi-aquatic, using the water for support. So I think the water is supporting the body and it's kind of poling itself along. There's no body scrape. But in order to make such deep impressions, the sediment must have been pretty wet and waterlogged.
This is like a kind of action replay of an instant in time about 370 million years ago. And it actually shows us what an animal was doing at that time.
These small steps are the marks of a great revolution for life on Earth. Our ancestors had arrived on land, and for the first time, our family album contained creatures that could crawl, walk, or run along the water's edge. Land was the final frontier. Leaving the shelter of life beneath the waves, animals had to adapt to a strange and hostile world. They came, they saw, and they conquered. Some of the first animals on land were like fish out of water. Modern monitor lizards show us how reptiles, sporting innovations like jaws and legs, flourished on land. Their stronger limbs made them into all-terrain vehicles. They could even reproduce on land by laying eggs, which were like nutrition-filled cradles for their developing young. Few obstacles could stop hungry reptiles. Certainly not trees. They could catch prey living high off the ground. Even small mammals. In time, these new animals would grow to great size. In pursuit of their next meal, they could go nearly anywhere, even returning to the water in search of prey. But another group of reptiles would diverge from the family tree and find a new way to move. These animals abandoned the ability to walk across the land and began to slither. A modern king cobra is still a worthy match for any adversary, even the ferocious water monitor. While they don't have limbs, snakes have their own secret weapons. Many of their talents originate from their jaws. No other creature accomplishes what a snake can do with its mouth alone. Without the help of limbs, it still needs to catch, pin down, kill, and eat its prey. A king cobra's usual fare is other snakes, like this rat snake. The cobra's lethal venom quickly immobilizes its scaly victim. One bite is all it takes, and then the cobra just holds tight as the poison takes effect. For us, eating without hands would be a messy proposition. But the snake solves the problem with its all-purpose jaws. Its teeth face backward, allowing the cobra to draw the victim directly down into its stomach. The cobra is ready to rest. It will sleep for days as it processes the meal. The cobra is lethal, but it is dwarfed by an elusive giant, hidden in the hyacinth swamps of Venezuela. These murky waters are home for the largest snake in the world. An anaconda waits patiently in the swamp for its next victim. The anaconda's favorite tactic is ambush. It will even attack jaguars. But the target this time is a capybara, the world's largest rodent. The snake is most comfortable in water. It can remain submerged for over 10 minutes as it glides into position. Jaws, devices that enabled our relatives to become predators, are spectacularly evolved in the anaconda. The giant snake's jawbones are so flexible that it can stretch its mouth around prey like a capybara, twice the size of the snake's head. With a full stomach, the anaconda can go for a year or more between meals. With skulls and jaws, animals would rise to the top of the food chain. The members in our family album would develop one dazzling design after another. Half a world away, one man has created an unlikely shrine in San Francisco, California. A shrine celebrating the feature that truly sets vertebrates apart: their bones.
When I went on my honeymoon trip in 1954 and saw the fantastic skeletal mounts in the Natural History Museum in New York, boy, that really settled it. Bones were fantastic. And once I started seeing bleached bones lying out in the fields there, I started collecting them. And by the time I got back to San Francisco, and my little convertible was filled with the skulls and pelvises and skeletons of all kinds of animals. And after, 40 and some odd years, I'm still doing it.
The curator of this private museum is Ray Bandar. He's a retired biology teacher who finds art in the creations of evolution.
They're nature's grandest sculptors. They're magnificent pieces of architecture. They have shape. They have texture. And they're very dynamic.
To some, Bandar's endless quest for animal bones borders on the ghoulish.
As far as collecting skulls and bones, some of my family members thought it was a little bit weird But it does make me proud that many of my friends and acquaintances, they really appreciate the collection. Artists have been here drawing and painting bones, as well as scientists and graduate students doing studies.
Bandar's Catacomb of Skulls is a testament to the diversity of our cousins. Skulls and jaws are among nature's most elaborate creations, and they tell a fantastic tale. But if sheer size is the measure of things, there is one group of animals that stands above all others. Dinosaurs were the largest animals ever to walk the earth. Like us, they shared the genetic legacy of little Amphioxus. They also shared the ravenous appetite of the reptiles. Some dinosaur groups got larger and larger over millions of years. But how did they get that big?
When you're standing underneath the Apatosaurus, you look up and you're looking at this organism that is an amazing piece of work. It's got a neck that looks like a suspension bridge with a head on one end and a tail on the other, a neck capable of sustaining an enormous amount of weight. It's got legs built like columns of a Grecian temple to maintain that weight. It's an eating machine with a huge rib cage to allow for a big stomach, big intestines, everything else. And it's a really amazing expression of the complexity of nature. Well, dinosaurs exhibit several different trends that are common throughout vertebrate life. One of them is a trend toward gigantism. And to be giant, you have to have a lot of support for your body. You can't just be a sack of water walking around.
The Big Sky country of Montana was once a dinosaur stomping ground. Here, paleontologist Christy Curry Rogers searches for fossilized remains of the thunder lizards. Curry Rogers suspects that her finds contain clues to the dinosaurs' gigantic proportions.
For a number of years, people have thought that dinosaurs might have taken 100 years to reach their adult size, or even more than that, 120 years. And my work is focused on how dinosaurs were growing, and I'm realizing that they didn't grow like that at all.
Bone is an extraordinary building material. Because it is living tissue, bone can respond to increased weight and stress by becoming thicker, growing. But the bones of most modern reptiles grow very slowly. So scientists believe that dinosaurs, too, grew slowly. Curry Rogers saw things differently.
There's a good evolutionary reason for growing quickly. If you're a small, juvenile individual and you're running around and you're being chased by predators on a daily basis and you're fighting for your life, it makes sense that you have to grow big to maintain your existence, basically. You have to grow fast so you can beat out the predators and be an adult and reach sexual maturity in time to actually reproduce and send your genes on through the gene pool.
In order to determine how quickly they grew, Curry Rogers looked deep within the bones themselves. She realized that, like tree rings, bones preserve a detailed record of growth rate.
You can look at the outside of a bone and it can give you an idea of external things that are going on. But to really read the story of an animal's life, you have to look at the inside. The first thing you do when you want to look at a dinosaur bone under a microscope is you have to cut a chunk out of a bone somehow so that you have a workable piece. And usually that piece lies right in the center of the bone because that's where bones start growing and they grow throughout the life of a dinosaur at that point.
To get at this evidence, Curry Rogers cuts a wafer-thin cross-section of a massive bone. The cross-section is ground 1/10 of a millimeter thin. This slice actually provides a view back in time.
After all the cutting and grinding and polishing, hours and hours of finger grinding off work, we end up with this beautiful thin section of a dinosaur bone. The first time you place a slide of a bone underneath a microscope, you're the first person that's ever seen what the inside of that bone holds and the story that it tells. You can see a snapshot of everything that happened in that animal's growth history up to the moment that it died.
The crucial snapshot will reveal arrangements of light in the bones, patterns created by blood vessels. If the size, shape, and placement of the patterns is uniform, the animal was growing slowly. But the evidence points the other way. She finds chaotic designs of light. The sizes and shapes are dissimilar, their placement irregular.
Just by looking at that very basic thing, the pattern of blood vessels, we can tell that dinosaurs were growing much faster than modern reptiles like crocodiles and lizards and snakes grow. And so if you can imagine a dinosaur that begins from an egg that's only about the size, a little bit larger maybe than a grapefruit, growing to an animal this enormous, it could have done it in about 10 or 12 years. And the bone remodeling that we see and the great amounts of vasculature, blood vessels and nerves that are supplying these bones tell us that this animal was growing very quickly and it was changing throughout its life.
Growing fast early in life, just as we do, dinosaurs rose to unprecedented heights. Towering over the earth, the terrible lizards once ruled supreme. But their giant size would prove to be a disadvantage. Their domination of the earth came to an abrupt end. "65 million years ago, an enormous asteroid crashed into our planet. The resulting cataclysm wiped out over half the animal species and nearly all of the large animals on Earth. Emerging from the shadow of the dinosaurs were small, furry creatures. They were the mammals, and they would inherit the Earth. The disappearance of the dinosaur predators meant opportunity for the mammals. They fanned out into a world ripe for the picking. And their bodies would soon adapt to take full advantage of the chance that lay before them. Today, mammals are the largest and most powerful animals on the planet. But that power comes at a price. Warm-blooded mammals like us have metabolisms that require constant fuel. Mammals replaced the dinosaurs as the Earth's most voracious consumers. The constant need to feed would shape our bodies and brains. Gradually, we became the most intelligent animals, adapting brilliantly to life on Earth. Elephants usually move slowly, but they are complex animals and highly social creatures. They're tetrapods, but with a useful extra limb. At times, their trunks function almost like our hands and arms. Elephants travel in family groups, led by the mature females. Within the family, elephants, like people, will form lasting bonds. The herd migrates across a vast range, moving from feeding site to feeding site. The family matriarchs remember the best feeding areas and watering holes. Like many large mammals, elephants reproduce slowly. Their calves are vulnerable and immature. Each one will nurse for more than a year. Young mammals, unlike many other animals, depend on their mother's milk and care. The herd acts as a team to protect each precious calf. This gives the young elephants time. In that time, they learn how to act like an elephant. Throughout a prolonged childhood, much like our own, a young elephant has years in which to play. Being a young mammal looks like fun. Play has been a critical element in the success of the mammals. We learn how to master our young, awkward bodies by exercising and mimicking the adults. Not only does play strengthen the body, it teaches us just what our bodies can and cannot accomplish. Through play, we learn how to get along. And it's a good idea to play at being an adult before the stakes are for real. At some point in time, one group of mammals took to the trees. This new habitat would have a profound impact on the course of evolution. The constant visual challenge of feeding in or scampering through a three-dimensional world favored an increase in the mammal's brain power. Living the high life, their hands, precursors of our own, became essential tools with which they could grasp or snatch a meal. Our closest animal relatives still live in remote forests. We are more closely connected to one group of primates than to any other animals. They act like us, even look like us. We see in them a pinnacle of social behavior. The increase of intelligence, the dawn of a similar consciousness. Instinctively, we are drawn to them. They are the great apes. They have evolved into thinking, feeling creatures. They nurture their own kind. They pass along social skills. We have shared an epic journey with them. Our long, common history diverges in only the last few moments of evolutionary time. Like us, they learn. They mimic. And they remember. We have so much in common, but the differences are profound.
Toda la vida estaba en el mar, pero había muy poquita vida. Entonces era el mar.
Our large human brains allow us to speak to each other. and write down what we have learned, passing on knowledge from generation to generation. Our intelligence separates us from the other animals on Earth. We alone seek life's meaning and ask the big questions. Where did we come from? How did we get here? We are a species that struggles to make sense of things. We have invented incredible tools that bring us closer to the answers.
Which one, Martin? Probably the larger of the two? You like the pink one, huh?
He's a nice color.
We use all of our knowledge and technology in the attempt to capture a glimpse of the big picture. We alone investigate and have come to appreciate the successes of other species. In piecing together the lives of so many other animals, we have come to recognize the narrative of a fascinating story. It's a story that began long ago.
Everything that's walking around on the planet today basically had very humble beginnings in the oceans. There are features that are common to all living organisms, and you can document the changes that have occurred in those organisms and also look at the commonalities and really develop an interesting picture of the history of life.
We share our modest origins with every animal, from the bizarre to the common. Over hundreds of millions of years, our genetic instructions have taken us down different paths. We are not the sole survivors of the great journey of evolution.
I never cease to be amazed by the diversity of animals and plants and the sort of tricks that they get up to see the sort of weird and wonderful, bizarre forms that animals can achieve. They really defy the imagination.
I think it's really important to remember that every living thing is so amazing and incredible because it is so well adapted to live in the planet and be around today.
As the eminent biologist E.O. Wilson wrote, humanity is exalted, not because we are so far above every other living creature, but because knowing them well elevates the very concept of life.